What is up, young chemists? Mr. Rosen here. Today we are going to talk about complete and net ionic equations. This is in our unit on solutions, and writing complete ionic equations is really a more accurate way to represent how the reactants and products are actually existing in solution. So usually when we write a chemical equation, that's really what I guess you would call a molecular equation, molecular chemical equation. But if we're working with solutions and we have two solutions, let's say they're water-based solutions, and they mix and one of the products forms a solid, what's called a precipitate, and the other stays dissolved in solution, it's sometimes useful to break that down so that you can see what ions are in solution and what ions are not. So a complete ionic equation better describes the state of all the reactants and the products. The net ionic equation includes only the ions involved in the reaction, which is the formation of a solid, the formation of a precipitate. The other ions, the ions that are not included, are what are called spectator ions. They are not involved in forming the solid, so they're not included in the net ionic equation. The easiest way to show this is just to break down some example problems. This does require us to use some skills that we've learned from really like throughout the year. Things like predicting the products of a chemical reaction, forming neutral compounds, balancing a chemical equation, knowing the charges of the ions on the periodic table. So we're going to go through some examples and hopefully get the hang of it. Once you do, these aren't quite so bad. So it says how to predict precipitates when solutions of two ionic compounds are mixed. So step one, write the reactants as they actually exist before any reaction occurs, remembering that the salts dissolve and separate as ions. Two, you do a double displacement reaction, most typically, or maybe it's a single displacement, but usually it's a double displacement reaction, and you exchange the cations, or the two metals, or the two positive ions, and that will give you your products. And then we're going to use a solubility table to see if any of our products are solids or if they stay dissolved in solution. So this is our solubility table. In some chemistry classes and in AP chemistry, they make you memorize the solubility rules. We're just going to be using a solubility table. And on here, you either see AQ, which means that will stay dissolved as ions in solution, aqueous, or S, which means solid, meaning it will not dissolve in water. S means solid, does not dissolve in water. All right, that's a precipitate. So let's do some example problems. This is the easiest way for us to figure out what these equations mean and how they work. So the first thing we're going to do is complete our molecular equation. So we have two reactants. We have PbNO3 in parentheses 2, right? This is called lead 2 nitrate. And we have KCl, potassium chloride. Now we have to figure out what are the products going to be of this reaction. So it's a metal, nonmetal, metal, nonmetal. That's a positive section, a negative section, a positive section, a negative section. Now, this is going to be a double displacement reaction, which means the positive section of one is going to switch places with the positive section of the other. So Pb and K are going to switch places, so that Pb is now going to be with Cl, and K is now going to be with NO3. Now, here's an important thing. I start by combining just one of each. Now, yes, you see how NO3 is in parentheses 2? Sometimes it's tempting for students just to take this whole thing and bring it to the other side. But if this says AQ, right, if this says AQ, that means that this is dissolved in water. And NO3, 2 is not floating around. What it means is you would have a PB ion, and then you would have a nitrate ion, and then you would have another nitrate ion. And these are all just floating around in solution, right? So if they're going to form a product, one of these things can link up with whatever other ions there are. These two nitrates don't have to stick together. They're not sticking together in solution. They're floating around individually. So I just start by putting one of them with one positive with one negative, one positive with one negative, and then I form neutral compounds, okay? So on the periodic table, this goes back to knowing the charges on the periodic table. Column 1A, these are positive 1, okay? 2A are positive 2. Over on this side, our noble gases, that's 0. This is negative 1. This is negative 2. Negative 3. This is positive 3. Plus 4. Minus 4. So these are just sort of general trends for ions. And the elements in the middle, these form, various charges, or called type 2 metals. So when we're looking at our example problem, potassium is in column 1A, it has a charge of +1. Okay? Chlorine is in column 7A, it has a charge of -1. So +1, -1, that's a neutral compound, right? Now over here, nitrate is a polyatomic ion. Nitrate is a polyatomic ion. If we're looking at the back of our periodic table here, I have a list of some common polyatomic ions. Nitrate right here is NO3, has a charge of -1. Okay, nitrate has a charge of -1. So if nitrate has a charge of -1, and there are two of them, that means that this part is -2. So this part has to be +2. So lead is +2. Nitrate is -1. So when we're forming neutral compounds, if chlorine is -1 and lead is +2, this is not a neutral compound. Pb is +2, Cl is -1. We have to have two chlorines for it to be neutral. K is +1, nitrate is -1. So +1 and -1, this is neutral. So we've formed neutral compounds. That's good. Now, this is not done yet because we have to do a couple of things. We need to figure out if a solid has formed. Any reaction has occurred. Is this a solid? Is this a solid? Let's do KNO3 first. Potassium nitrate, KNO3, potassium nitrate. So if we look at our solubility table, potassium nitrate, okay, potassium is here, nitrate is here, AQ. AQ means it's going to be dissolved in water, aqueous. So potassium nitrate is AQ. That will stay dissolved as ions in solution. Pb is lead, and Cl is chlorine, which we call chloride. So lead chloride, the charge of lead is 2, so we call that lead 2 chloride. So here we have lead with the Roman numeral 2, and then chloride, lead chloride. Look at that. What do we have? S. S means it's a solid, a precipitate, does not dissolve in water. So, lead chloride, S. That is our solid. That's our precipitate. Now, at this point, we have predicted our products, we've formed neutral compounds, and we figured out if a solid forms or not. Okay, that's good. We still have to balance the chemical equation. Okay, so now we're balancing. 1 PB is on this side, 1 PB is on this side, 1K, 1K, 2 CLs, 1 CL here. So things aren't balanced in this equation. If we put a 2 in front of this, now we have 2 CLs, and here we have 2 CLs, so that's balanced. But that gives us 2 Ks, and over here we only have 1 K. So we have to put a 2 in front of this. And doing that actually gives us 2 nitrates, which is good because we have 2 nitrates over here. So now we've balanced the equation. Okay, so this is our molecular equation. Okay, I know I wrote these charges in here, but really, those charges right there should just be ignored, right? If we were covering those up, this would be our molecular equation. PbNO3 in parentheses 2 plus KCl gives us lead chloride and potassium nitrate. We balanced the equation, predicted it. Okay, so you can't do the rest of the stuff without having a balanced molecular equation. Now, the complete ionic equation takes this and it breaks it down into its ions, and you show the charge and state, meaning solid, liquid, gas, AQ, of everything for the reactants and products. So, PB, right, if this is AQ and this is AQ, as I mentioned, that means that these things are going to be floating around as ions in solution. Okay, so writing the complete ionic equation, PB has a charge of positive 2, and it's AQ. Plus, I'm going to have 2 nitrates. So I'm going to write a coefficient of 2, and then I'm going to have NO3, which has a negative charge, AQ. So this is this broken down into its ions, right? If this is AQ, meaning dissolved in solution, we're going to have a PB, and we're going to have 2 nitrates. So we have a PB, which has a charge of positive 2, and we have 2 nitrates, which has a charge of negative 1, right? This right here is this, right? A PB, a nitrate, and another nitrate in solution, floating around in water, right? So I wrote out PB plus 2 nitrates plus, we're going to have 2 potassium ions, which have a charge of positive 1, that's AQ, plus 2 chlorine ions. Those are our reactants, right? A lead ion, 2 nitrate ions, 2 potassium ions, 2 chloride ions. AQ, 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 AQ. Notice I have the charge of every one of the ions, I have the state of every one of the ions, and I have how many of them I have using coefficients. Okay. Now, you do not break the solid down into ions because it doesn't exist as ions in solution. The solid stays intact. So I just write PbCl2S, right? That stays intact. Then I have 2 nitrates, 2 potassiums, so I write 2 Ks. And I have 2 nitrates. So this is our complete ionic equation. We have all of our ions in solution present before, and then afterwards we have the formation of a solid which stays intact, and then we have 2 potassium ions in solution and 2 nitrate ions in solution. Now, the net ionic equation includes only the ions that go into making the solid. That is, what plus what gives you PbCl2. So PbCl2 solid goes on this side. And on this side, we're going to have Pb plus 2 chlorines, and that gives us our solid. It includes only the ions that go into making the solid. Now notice what's not included. If we look in this equation, here we have 2 potassium ions floating around in solution, and afterwards we have 2 potassium ions floating around in solution. Also, we have 2 nitrate ions floating around in solution before, and afterwards we have 2 nitrate ions floating around afterwards. So both potassium and nitrate are present floating around before and afterwards. They didn't do anything. They weren't involved. They just sat back and watched. These are called the spectator ions. Okay? They are not included in the net ionic equation. So this is writing a complete and net ionic equation. We're going to do a couple more examples, and hopefully you start to get the hang of it, okay? But before you can do the complete and net ionic equations, you have to do the molecular equations completely and correctly. So here we have BaCl2 and sodium with sulfate. So again, it's positive section, negative section, positive section, negative section. Metal, nonmetal, metal, nonmetal. We're going to take our positive ions and switch them. Okay, so Ba is now going to be with SO4, and Na is going to be with Cl. So Ba is with SO4, so I'm going to write BaSO4. And Na is now going to be with Cl. Now, again, notice here there's 2 Cl's and here there's 2 Nas. I did not write Na2Cl2. I'm just bringing one ion of each over. I'm making the simplest neutral compound. Okay. If this was in solution, you're not going to have a Cl2 floating around like this. Okay, you're going to have a Cl, and you're going to have another Cl, and then you're also going to have a barium. Okay, so individual ions will combine in the simplest neutral way. Now, looking on our periodic table, barium is in column 2A, so that means it's positive 2. Chlorine is in column 7A, that means it's negative 1. Okay, so I'm just going to go down and jot the charges of these. So barium is positive 2, chlorine is negative 1, sodium is positive 1, and SO4, sulfate, is a polyatomic ion. It's negative 2. So if barium's positive 2 and sulfate's negative 2, this is actually a neutral compound, plus 2, minus 2. And if Na is positive 1 and Cl is negative 1, then this is also a neutral compound. So those are both neutral compounds. Now we're going to see if a solid forms. Okay, so we have barium sulfate. Let's look on our chart. Barium sulfate. Okay, barium is here. Over, sulfate, barium sulfate. Ding, ding, ding. S. That means it's a solid. Barium sulfate is going to be a solid. That's our precipitate. So I write S. NaCl is table salt. You're probably aware that it will dissolve in water. Sodium and chloride. So sodium and chloride. This one's chloride. Sodium and chloride. There we are. AQ. So NaCl will be AQ. So now we predicted our products, and we made sure they're neutral, and we found our solid. We need to balance the equation, okay? This has two NAs, and we only have one over here, so I'm going to put a coefficient of 2. And doing that actually gives me 2 chlorines, which is good because I have 2 chlorines over here. And then 1 Ba and 1 SO4, those are balanced, right? So now it's balanced. So we have a complete molecular equation. It's balanced. We know our solid is the barium sulfate. Now we're ready to write the complete ionic equation. So we're going to break our reactants down into individual ions, right? We have Ba, which is positive 2 AQ, plus 2 chlorines, coefficient of 2, Cl has a negative charge, AQ. All right, so when that goes down, it breaks down into solution, we're going to have 1 barium and 2 chlorides. We also have 2 sodiums, 2 NAs, which have a positive 1 charge, AQ, and we have a single sulfate. So we write SO4, which has a negative 2 charge, AQ. Those are our reactants. Okay, notice, I have the charge of every ion, I have the state of every ion, AQ, 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 and I have coefficients for how many of them I have. The solid does not get broken down into ions because it's not broken down as ions, it's a solid. And then I have 2 sodiums and 2 chlorines. All right, this is our complete ionic equation. The net ionic equation includes only the ions involved in making the solid. So what plus what gives us barium sulfate? The barium ion, Ba, which has a positive 2 charge, and the sulfate ion, which has a negative 2 charge. So Ba, aqueous, plus sulfate, aqueous, gives us BaSO4, solid. Those are the ions involved in making the solid. We did not include, notice, look, here's 2 chlorines floating around before, 2 chlorines floating around afterwards, 2 sodiums floating around before, 2 sodiums floating around afterwards. Those are spectator ions. We don't include them. They're not involved in making the solid. Okay? Let's do a final example. It's a little bit of a, maybe a little bit of a harder one for our molecular equation. So we have K3PO4, and then we have CaNO3 in parentheses 2. So again, positive section, negative section, positive section, negative section, metal, non-metal, metal, non-metal. So K and Ca are going to switch places. Okay, this is a double displacement. So those are going to switch places. So that means that Ca is now going to be with PO4, and that also means that K is going to now be with NO3. We've actually already seen KNO3 in a previous problem, so you already know some stuff about that, but we'll get to it. So potassium has a charge of positive 1, and phosphate, PO4, that's a polyatomic ion. Phosphate has a charge of negative 3. Okay, phosphate has a charge of negative 3. So that makes sense, right? If K is positive 1 and this is negative 3, that's why you have 3 of them. That's a neutral compound. Calcium is positive 2 and nitrate is negative 1. Right, that's why we have 2 of those. So we have to form neutral compounds on this side, okay? Calcium is positive 2. Phosphate is negative 3. So this is not a neutral compound. To make it a neutral compound, it's actually, negative 3 and positive 2. This is a lowest common multiple thing. we actually have to put this in parentheses. Put a 2 outside of it. We have to put a 3 here. Okay, that is our simplest neutral compound for calcium phosphate. Okay, 3 calciums gives you positive 6. 2 phosphates gives you negative 6. That's a neutral compound. Okay, now potassium's positive 1 and nitrate's negative 1, so this is neutral. So those are our 2 products. They're neutral compounds now. We're going to see if one of these is a solid or not. Okay, potassium nitrate, we actually already saw that one over here. Right, potassium and nitrate is AQ. The other one was calcium and phosphate. So if we look at calcium and then we look at phosphate, ding ding, solid. So this is a solid and this is AQ. Now, the final thing is we have to balance the equation. Okay, we have to balance the equation. So there are 3 potassiums here. So it might be tempting to put a 3 in front of this one, but if we do, that'll give us 3 nitrates, and over here we have 2 nitrates. So that's not going to work. Okay. Now, looking at this one, we have 3 calciums, and here we only have 1 calcium. So we actually can put a 3 in front of this. Now our calciums are balanced. Now putting a 3 here means we actually have 3 times 2. That gives us actually 6 nitrates. 6 nitrates. So to have 6 nitrates over here, we have to put a coefficient of 6. And then that gives us 6 Ks. So over here, to get 6 Ks, because there's a 3, we have to put a 2 here. And this is good because it actually gives us 2 phosphates. And on this side, we already have 2 phosphates. So this is our complete molecular equation. The equation is balanced. We have our products. We know if a solid formed. Now we are good to go. We're ready to write our complete ionic equation. Here we go. Break it down. So if this is a 2 and that's a 3, that means we have 6 potassium ions. So I'm actually going to write a coefficient of 6 potassium ions. Each one has a charge of positive 1, AQ, plus 2 phosphates. So a coefficient of 2, PO4, has a charge of negative 3, AQ. Plus, I have 3 calciums, so 3 CAs, which have a positive 2 charge, AQ. And I have 3 times 2 is actually, again, 6 nitrates. 6 NO3s, which have a negative charge, AQ. So those are our reactants. 6 potassiums, 2 phosphates, 3 calciums, 6 nitrates. All of the charges are written, and all of the states are written. The solid does not get broken down, so I'm going to write Ca3PO4 in parentheses 2, solid, plus 6 nitrates, which have a positive charge, and 6 nitrates, 6 potassiums and 6 nitrates. Sorry if I said that twice. 6 potassiums and 6 nitrates. This has a charge of negative, and this is also AQ. This is our complete ionic equation. Notice I have 6 potassiums floating around before, I have 6 potassiums floating around afterwards. Same with nitrates. Those are spectator ions. We're not going to include them. We only include the stuff involved in making the solid. So we have our 3 calcium ions, which have a charge of positive 2, right, in solution, plus we have our 2 phosphate ions, and each of those have a charge of negative 3. All right, so 3 of these and 2 of these combine to give us Ca3PO4 in parentheses 2, as a solid. This is the net ionic equation. It involves only the ions that go into making the solid. The complete ionic equation shows all of the ions in terms of how many there are, the charge and the state, before and after, and the solid does not get broken down because it stays a precipitate, it stays a solid in solution. This has been a video about complete and net ionic equations. There's kind of a lot of little steps to it with all the charges and stuff, but practice makes perfect. Keep it up. Work, work, work. See you back in class.